Welcome back to the solutions manual. In this video, we will solve the problem 1-47 from RC Hibbeler Mechanics of Materials 8th edition. According to this problem, we have to determine the average shear stress developed in pins A and B of the smooth two-tine grapple that supports the log having a mass of 3 megagrams. Each pin has a diameter of 25 millimeters and it's subjected to double shear. Now to solve this problem, first of all, let's calculate the weight of this log. We have to use it later on. So weight is equals to mg. The mass is 3 megagrams, so we have to convert it into the kilograms. So we have to divide it by 1000 and multiply it by 9.81. The weight of the log comes out to be 29430 newtons. Now if I just draw the free body diagram of this log, the free body diagram would look something like this. I have a normal reaction from the grapple onto the log. Similarly, another one. And I have a weight acting in the vertically downward direction. So let's label them. So this right here is the weight of the log, which we have calculated as 29,430 newtons. This is the normal reaction R, and since the grapple is symmetrical and the log is also symmetrical, so the other normal reaction is also the same, so R. Now we can resolve these normal reactions into their components. So we have one vertical component and one horizontal component. Similarly, one vertical component and one horizontal component. Let's label them as well. So this right here is R cos 30. This is also R cos 30. The vertical component is R sin 30. And this one is also R sin 30. Now to calculate the value of R, I can apply summation of forces in y direction equals to 0. I'm considering up direction as positive. So we have R sin 30 plus another R sin 30 minus W equals to 0. So when we simplify it, we have 2R sin 30 equals to W, which is 29,430 newtons. So R comes out to be 29,430 divided by 2 times of sin 30, and the value of sin 30 is 0.5. So R comes out to be also the 29,430 newton. Now we have to calculate the shear forces in the pins A and B to determine the average shear stress. So for our next analysis, since the grapple is symmetrical about the y-axis, so we will do the analysis only on the left arm of this grapple. Let me shade it. Only on this arm of the grapple. So let me copy this image. So if we just consider the left arm of the grapple, and if I draw the free body diagram, the free body diagram would look something like this. So I have one horizontal support reaction at pin E and one vertical support reaction. Similarly, I have the normal force because of this log, which we had assumed as a compressive force. So now it will act towards the grapple. Similarly, I have a tensile force because of this rod AB. Let's label them. So this right here is EX and this is EY. This is R, TAB. Now I can resolve the TAB and R into their respective components. So I have one vertical component and one horizontal component. Also, we have to resolve the normal force R into its components. So I have one horizontal component and one vertical component. Let's label them as well. So this right here is R cos 30 and this is R sin 30. So I hope that the free body diagram for the left half of the grapple is clear to you all. Even though if you have any query, then feel free to ask in the comment section and I will answer it as soon as possible. So let's get back to the problem. Now we have to find the TAB force. So for the TAB, I can do summation of moments at point E equals to 0. I'm considering the counterclockwise direction as positive. EX and EY will not produce any moment about point E because they are passing through it. So they have no momentum with respect to the point E. Also the vertical component of the normal force R, its line of action is passing through the point E. If you trace it back, so R sin 30 will not produce any moment about the point E as well. R cos 30 is trying to rotate the grapple in the clockwise direction. So the moment produced by this R cos 30 will be taken as negative. And the moment arm is this perpendicular distance. Let me draw it. And the moment arm can be found by subtracting 1.2 from this distance, the vertical distance. Let's call this x. So if we consider this triangle, this right here is 30 degrees. This is the vertical distance x, and this is 0.4 meters as given to us in the diagram. The radius of this log is 0.4 meters. So x is equals to 0.4 sin 30. So the moment arm is 1.2 minus the x, which is 0.4 sin 30. Similarly, the vertical component of the TAB, which is TAB cos 20, is trying to rotate the grapple in the clockwise direction. So the moment produced by this TAB will also be taken as negative. So negative TAB cos 20, and the moment arm is this horizontal distance, which is 0.2 meters. Now the horizontal component of the TAB force, which is TAB sin 20, if I draw its projection at the tail of the vector TAB, let me label it as well. This right here is also TAB sin 20. Now we can see that TAB sin 20 is also passing through the point E. So it will not produce any moment about point E because it is passing through it. So it has no moment arm with respect to the point E. So TAB sin 20 will not produce any moment about point E as well. So equals to 0. Since we already know the value for R, so minus, that is 29,430 into cos 30 multiplied by 1.2 minus 0.4 sin 30 minus TAB cos 20 into 0.2 equals to 0. So when you simplify it and you solve it, the value for TAB comes out to be negative 135.61 exponent 3 newtons. Now we have to find the average shear stress in the pins A and B. So the shear force VA is equals to VB. VA is the shear force in the pin A and VB is the shear force in the pin B. And they are in turn is equals to TAB. Similarly, both of the pins have the same diameter. So cross-sectional area of the pin A is same as the cross-sectional area of the pin B. And in turn, they are equal to the area of the circle, which is pi d square upon 4. So pi into 25 millimeters, so 25 exponent negative 3, because we have to convert it into the meter, square divided by 4. So the cross-sectional area comes out to be 4.909 exponent negative 4 meters square. So the average shear stress in the pin A is equals to TAB, which is same as the shear force VA, divided by, since the pins are in double shear, it means they are in the twice of the cross-sectional area. So 2 times of the cross-sectional area of AA, pin A. So TAB is 135.61 exponent 3 newtons divided by 2 times of 4.909 exponent negative 4 meters squared. So the average shear stress in pin A comes out to be 138.13 exponent 6 pascals or 138.13 megapascals. Since in both the pins the shear force is same, the cross-sectional area is the same, and both the pins are in the double shear, it means average shear stress in the pin A is same as the average shear stress in the pin B. So in turn they are the same as 138.13 megapascals. So this is our final answer. So this is it for this problem. I hope you will find this video helpful. If you do, please make sure to subscribe to this channel and also turn on the bell icon for the daily updates. And if you have any questions or any doubts, then feel free to ask in the comment section and I will answer it as soon as possible. Thank you.